he is a postdoc, so he just finished the military service. So he free to go outside.
Right.
He's already getting doctor in the last years. So he cannot go outside because it's military service.
But I thought that's allowed. Yeah, it's academics. You work in
Academia is the doctoral program there, and military service is the exam. Not really, but it's there is a track that should stay somehow at least 3 years.
Not so bad.
The whole quiet. What are your origin?
So I was born in Hong Kong,
Hong Kong.
but I moved to Canada when I was 5. So I consider myself
It's quite expensive. Just one movie is more than 1,000. His salary is so 3,000. The study is 3,000. Yeah, American $30,000. Then it's sort of somehow survive.
yeah, I mean, will you be coming with them?
Right, good morning, everyone. It's a pleasure for me to start this Wednesday session, and I got a promotion to be a chair for today.
And the salary?
Tomorrow.
We talk about that next. Later. Right, our first speaker is Professor Alfred Hero from Michigan. He's going to talk about continuum relaxation for discrete optimization.
Thank you.
On. It's on now. First, I really have enjoyed the workshop so far, and lots of things to learn. Thanks, Raymond and Mila, for inviting me to speak. So what you're going to see in the next 40 minutes will involve some variational methods. You'll see some differential equations, partial differential equations. So there'll be some tangencies there. But the topic in terms of the imaging connection is connected to a slightly different context than what we've seen thus far at this workshop, in the sense that I'm going to be focusing on databases of images and using similarity measures to try to make inferences or partition databases of images into classes where one can say something about say the indexing or retrieval or different types of characteristics of the images in the database. So that will be the application. Okay, so and I'll touch upon some other applications of these types of discrete optimization problems that come out of this type of retrieval and indexing in other areas of imaging also. So image databases is the motivation. Then I'm going to talk about minimal graphs as a way to cluster or classify or index databases according to some similarity measures. And then I'll talk about some continuum limits, and that's where we're going to see the variational methods enter into the picture. And then multi-objective image retrieval will be one of the primary applications here, which, if I have time, I'll show how we've applied this to anomaly detection in a certain type of image set. So this, of course, is a body of work that would not have been possible without collaborators and sponsors, and these are just some of my collaborators and students and sponsors. All right, so in an image database, frequently one wants to use a measure of similarity between images in order to somehow make sense out of the relationships between the object and the database. So for example, in this database here, which is a very dear one to me because it's my mother and my grandmother's database of their paintings, one might want to take my grandmother's paintings up here and look at how they're related to my mother's paintings down here, see if there's any temporal relation. My mother started painting when my grandmother was mid-career, and if there was some sort of similarity transference, right, from one artist to the next by virtue of relationship. So that's certainly a motivation that makes a lot of sense from the point of view of genealogical research, and but it's also very challenging because in order to do this type of clustering, we have to define a difference between, the images of the artwork in this set versus this set, and be able to use that in order to sort of make sense out of the kinds of trends that that might exist over time or over the space of actual representations, right, of the artworks. So there's been a lot of work in applying mathematical techniques to extracting features from different types of images, art in particular. So we all know of the work of Ingrid Dochis, for example, who's looked at fraud detection and authentication for artwork. And there's the similarity measures are critical. And indeed, some of the natural similarity measures that might come up would be, let's just use some sort of L2 distance. Well, that's obviously not going to be very effective if you're interested in, for example, comparing color hue histograms, because as we know, comparing histograms in L2 is a very poor measure of difference between functions which are non-negative and sum to 1, because it overemphasizes the central concentrated part of the function and disregards the tails. And it's in the tails where often the most interesting comparative analysis can occur. And so one of the issues is to sort of come up with the right metric for comparing different images. And in the area of art indexing and comparison, there's quite a bit of work, notably by the Rutgers group of Saleh and El Gamal, who have proposed different types of non-Euclidean, including what's called the Kullback-Leibler divergence, which is equivalent to at least for in the asymptotic sense, for two very close histograms to a squared and weighted Euclidean distance. So this is not so difficult in terms of computation once you have your features. If you have 600 or 500 pieces of work to go through a similarity comparison, to try to build graphs of similarity and basically transit the similarity across time or across space of images. But if you take one of these images, and this is actually a sketch of my brother when he was about 7 years old, that we want to sort of compare to images within a larger database. And so here is the Google image database of several billion images. Well, now the computational aspects become very important, because you're effectively trying to form a list, right, of similarity, which is going to decrease monotonically across the database. And if you have several billion images, that's really going to be an issue of computational importance. And so we're going to be interested in doing these types of in this particular case, constructing lists or constructing clustering methods which can use similarity metrics in a very large-scale database. Okay, so another application, which I'm going to be discussing later on, is computing minimal paths through image databases, given a similarity metric. And so this is a very interesting paper that recently appeared by Alfred Hero in the computer graphics community, where you have a sequence of images and you basically want to sort of smoothly morph from an initial image to some final destination image. So an initial point to a final point, and in order to sort of be able to span out a continuum, or at least a quasi-continuum, relative to the density of the database of the objects as they move from one object to the next through a increasingly large distance from either object in the middle, and then getting progressively closer to each object, initial and final object, as you go to either extreme. So this is a minimal path relative to a list of similarities between all the images, and computing these minimal paths you can do, of course, with Dijkstra or fast marching or your favorite algorithm for minimal path computation. But if you have billions of images, this also can be very computationally expensive, of order, with the naive algorithm, the minimal path algorithm is order of the square of the number of objects in the database. Okay, so that's the setting for motivating this discrete optimization problem or set of problems over image databases. So query matching and retrieval, like the first example I mentioned, where you want to find elements in the database that are most similar to some query. That similarity can be measured in terms of a variety of mathematical metrics or pseudometrics, and you can perform the listing using shortest paths or nearest neighbors or what have you. Clustering and indexing the database for fast retrieval, where you want to find some partition and then a representative from the partition elements that can give you a sort of a multi-resolution or multi-scale hierarchical search, divide and conquer, where you now have log of the number of objects times the number of objects as the complexity can be accomplished by finding some min-cut, let's say, or morphing and dimensional reduction, as I said, which uses shortest paths. So these are all optimization problems over a discrete space of the number of elements in the database. And so we're going to, in particular, construct relative to a set of features for each image, which could be, as I say, histogram features or spherical invariant feature transform, SIFT features or Hog features, or any other features that you might extract from the image, are then compared using a similarity measure to form a graph by thresholding that measure where the edges will exist if the similarity is sufficiently large between images connected by the edges, and where each vertex corresponds to a given image. So in order for us to characterize what happens to these graphs in terms of their asymptotic properties for very large databases, so that we can somehow maybe seek to conquer this very large-scale problem of indexing or clustering or shortest paths, we're going to model these features as random variables coming from some unknown multivariate distribution, right? So the concept here is there's some big abstract space with a distribution of the images that are realized as independent, identically distributed image instances from this multivariate distribution, whose dimension will be as large as the dimension of the feature space, right? So n images here. All right, so minimal geometric graphs. Geometric, why? Because we're going to be looking at Euclidean or Euclidean-like similarity measures. We have a set of vertices, each image, with its, represented by its features, in some space which might not be a linear space, subspace, no linear subspace of the d-dimensional feature space. And then we build a graph over these points, these nodes, vertices being V and edges being E. The similarity between two pairs of nodes is going to be the Euclidean distance. And then, of course, we can construct an adjacency matrix associated with the graph if we threshold, right, these edges. And then we can of course also define things like degree of the vertex, which is the sum, the row sum of the adjacency matrix. The adjacency matrix is going to be symmetric since the similarity measure is also symmetric. What we seek to optimize is some length functional. So this could be for clustering. This could be a k-nearest neighbor graph or a minimal spanning tree. For shortest path, it could be the objective function that consists of path length. But here what we're going to do is we're going to allow the use of similarities which are not simply linear in the Euclidean distance, but are Euclidean distance raised to some power gamma, right? So that we can accommodate things like the Kullback-Leibler distance or higher order measures of similarity that capture relationships that are geometric, but geometric to some degree characterized by this power expansion, if you like, of the similarity measure that we choose. And here, so gamma is going to be greater than 0. It's called the edge exponent. And so k-nearest neighbor graph is an example of this discrete optimization problem where L now depends on this edge exponent. It's the minimum over all graphs such that the degree of every node is greater than k. The k-nearest neighbor graph, therefore, gives you a, in general, non-connected graph that doesn't necessarily span all the points, but it's a forest over your database. And as you increase k, you increase the connectivity, right? And so these types of graphs can be have been used for all kinds of different applications. Computational complexity is of the order of n log n. So just some of the applications that we're all familiar with are spectral algorithms based on k-nearest neighbor graphs, which use the graph Laplacian to accommodate the fact that the space where the image features live may not be linear, right? It may live on some surface, and then one can discover the surface and do things like interpolation or extraction of surface properties or clustering by performing an eigendecomposition on the similarity matrix W, that is of all the similarities between pairs of xi's, where you subtract the sum of the rows in a diagonal matrix and do the eigendecomposition, as I say, and then you can reconstruct a lower dimensional version of the data, use spectral clustering, and so forth. Minimal spanning tree is another type of graph which is guaranteed to span all the points. It has n-1 edges. It's of order n squared log n. The minimal spanning tree can be used for clustering, again, like I'm showing here, where you cut the largest edge. You have two clusters that are far apart. Computational complexity is on the order of n squared log n in general. It's been used for doing things like building image representations with image pyramids, surface rendering, and segmentation, and so forth. So these optimization, discrete optimization problems are ubiquitous, right, in these types of imaging examples. Shortest path is a problem where you seek to find the shortest distance in terms of similarities over a graph. So here is a k-nearest neighbor graph with k equals 6, so each node has degree 6. You have an initial point, xi, over here, and a final point, xf, over here. And then through this graph, you want to find the path that minimizes the distance, right? The total length of the path from xi to xf. And of course, one can choose different graphs to construct this shortest path. One can choose the complete graph, in which case the shortest path is always a straight line, right? Complete graph is a graph that has every vertex degree is n minus 1. So every neighbor, every node has n minus 1 neighbors, and no node is more than one hop away from any other node. But there are other possibilities, k-nearest neighbor and minimal spanning tree and so forth. And I should say the shortest path in terms of gamma equal to 0 to 1. So I'll mention that in just a minute. So the shortest path algorithm has been used in lots of applications, one notably in isomap for dimensionality reduction to approximate the local curvature. One uses the k-nearest neighbor neighborhood and the graph Laplacian approximation to the Laplacian-Pastrami operator, and then you can do shortest paths through your database and come up with these sort of visually similar trajectories or tours through the database that intuitively make sense. So back to the comment I just made on the shortest path through the complete graph, and that's what I'm going to be focusing on here for the asymptotics, is if you choose the Euclidean distance as your criterion for measuring total path length, so that means edge weight exponent gamma equals 1, then as I said before, the shortest path between any pair of points is just a straight line, because through the complete graph, through the Pythagorean construction, or the Archimedean axiom of shortest paths, the shortest path between any 2 points in Euclidean space is a straight line, right? If you choose a Euclidean distance squared, like would be associated with this other histogram similarity measure that I mentioned in the beginning, the divergence, well then it's no longer true that the shortest path is a straight line, right? And that's simply because you can get a shorter distance because the distances between pairs of points along the way is in general less than 1. In this example, we're on a 0, 1 plane, so therefore, by summing up a number of numbers that are less than the Euclidean distance, the Euclidean distance squared, you get a shortest path, which is actually a jagged path through the set of points. So this is interesting because it says that indeed the geometry, the intrinsic geometry of the space can be characterized by a complete graph if you use a power of the Euclidean distance where that power is greater than 1. If the power is less than 1, you still get a straight line path as the minimizing path, right, between any pair of points if you're going through the complete graph. But here, the shortest path is, as I say, no longer the straight line path. Now this has interesting behavior when you go from a uniform set of points, this is uniformly distributed features, 2,000 features, to a Gaussian, or non-uniform in general, but here Gaussian set of features. So the shortest path, again, if you use a straight Euclidean distance as your path length criterion, is a straight line between the 2 points. if it's the square or any gamma exponent greater than 1, the shortest path has this kind of curvature to it where it tends to want to go towards the center of the distribution, where points are closer together. The closer the points are, you get the benefit of, an order of magnitude, a squaring of the distance. So you have an advantage of going through denser points than non-dense points. This is analogous to, if you like, the sort of Archimedean, or if you fast forward 1,000 years or so, a couple of thousand years, Newtonian physics versus special relativity physics, where paths through very dense massive regions tends to bend if you're talking about a photon following a path through space. So we have this relativistic regime where if you have dense samples in one region and not so dense in another region, the shortest path tends to try to go through the denser region. So can we explain this? Can we explain this this lensing effect, right? This massive, dense field lensing effect? Can we explain how these minimal spanning or Krainer's-Neighbor graph length functionals behave as you respectively take the limit of the number of features, that is the number of objects in the database, becoming very large. And so that's really the core of the talk. To motivate this, if you just do an experiment, you can see that the minimal spanning tree, if you look at 128 samples over the unit square, following the uniform distribution, versus a non-uniform distribution that's concentrated in the center, that the overall spread of the points is going to determine the length, right, of the graph, of the optimal graph. So in the minimal spanning tree, the length of the minimal spanning tree for the uniform distribution is greater than the length for the more concentrated distribution. Right? So that suggests that these minimal spanning or combinatorial optimizations that seek to minimize length in some way is somewhat like a measure of the concentration of the distribution, right, over the feature space. And indeed, you can look at the large N behavior, so N being the number of objects. If you look at this non-uniform distribution with a triangular, two-dimensional triangular distribution with a maximum in the center of the cube versus the uniform distribution, they both go off in terms of the length, as the length of the minimal spanning tree, to infinity, and it looks like they have somewhat different rate constants, but the factor n has the same exponent. Indeed, if you normalize by root n, so there's the exponent 1/2, these are going off sublinearly to infinity at rate root n. If you normalize by root n, you get asymptotes of the uniform and triangular minimal spanning tree length as n gets large. And these asymptotes, in fact, can be characterized exactly, and that, in fact, was done back in 1959 for the uniform distribution by Beardmore, Haltons, Hammersley in a paper in the Cambridge Philosophical Transactions, where they established that as long as the distribution is continuous, so Lebesgue distribution, there are no atoms or concentrated masses, that and if the subset on which the distribution is supported is compact, then the minimal spanning tree will converge at a rate n to the power of d minus gamma over d. It's always a exponent that's less than 1 if gamma satisfies these conditions. And the constant, the rate constant, is precisely this function of the underlying density of the points. That was shown later on by Michael Steele, who I don't have him referenced here, but in the early 70s, he showed that he could generalize this from the uniform distribution that Beardwood-Halton-Hammersley proved this theorem for. And this is proportional to the entropy. There should be a log there. That's a typo. An entropy function, which is called the Rényi alpha entropy, where alpha is equal to d minus gamma over d. It's a measure of, the entropy is a measure of the spread, right? So indeed, the intuition here was correct that the minimal spanning tree or k-nearest neighbor graph for which this theorem applies is a measure, the length of those graphs is a measure of the complexity in terms of concentration, right, of the density over its domain through specifically the entropy function. So this suggests that we can use the log of the length function of the minimal spanning tree or k-nearest neighbor graph to form an estimate of entropy, right? So it's a new way to estimate entropy that then provides our first continuum limit for discrete optimization, right? If you're interested in entropy and you use minimal spanning tree to estimate the entropy, well, you can do it a lot easier by just plugging in a density estimate, right? And then we have rates of convergence that we showed a while ago. The way that this mechanism works is based on basically a number of principles that govern this the length function that's defined relative to the optimization, to the discrete optimization. So this continuum limit is very general, shown by Joe Jukic in 1998 in this beautiful book of his probably theory of classical Euclidean optimization problems, where any graph construction like k-nearest neighbor or minimum spanning tree that's quasi-additive, continuous Euclidean it will satisfy this limit. And so that includes the traveling salesman problem, the Steiner tree, and a lot of other types of graph constructions. And so you get this continuum limit under this quasi-additive continuous Euclidean length functional construction. Certain constructions don't satisfy this limit, or at least they don't satisfy these principles, but many do. So translation invariance and homogeneity is one of the properties of this class of length functionals, that is, graph constructions that are based on optimization of a length functional. So translation invariance simply means that if you have a set of points over which you're constructing the graph, and you shift all the points by the same amount by a constant translation, then the length function doesn't change. And if you scale all the points by saying mapping the unit square into a square of side 3, right, then the length only changes by a constant c, which is equal to that scale factor, raised to the power gamma. That's the homogeneity condition. And there's a null condition. Subadditivity and superadditivity basically is a kind of partitioning heuristic that says that if you can construct graphs over small portions of your space, if you partition the space into m to the power d cubes of length m each, then the length of the graph that you construct by minimizing L gamma over the set of edges that you include in the graph can be approximated by the sum of the lengths of the graphs that you construct over the smaller number of points, right? So this is the partitioning heuristic that led to KD trees and Karp's approximation to the traveling salesman problem tours by partitioning, and Aurora's traveling salesman forest construction methods and so forth. So this is where the quasi-additive property comes in, and then continuity is a property that makes a lot of sense. That if you construct the tree or the graph over the union of two sets of points, then the graph length will increase by an amount which is upper bounded basically by the cardinality of the number of points that you've added to the initial set f raised to this power, d minus gamma over d. So the proof of the Beardwood-Halton-Hammersley theorem is, it's not a one-liner, but it's instructive just to sort of go through why it works. There are really two parts of it. You start off with a uniform distribution, and then you show that over the uniform distribution, the length of the middle spanning tree behaves as some constant times the number of points in this power. And that makes sense because the average distance between n points in the d-dimensional cube is going to be n to the power minus 1 over d, right? The dth root of n is inversely proportional to the distance, average distance between these points. You put n points into a d-dimensional bounded domain. The points on the average are going to be 1 over the square root of d apart. And since there are n points in the minimal spanning tree or the k-nearest neighbor graph will connect those points, the length of the minimal spanning tree will be n times the average distance, right? So that's n times n to the minus 1 over d to the power gamma. So don't forget we're raising this to the power gamma. So you get the total length is n to this power. So it makes total sense when you look at it that way, right? Geometric sense. And then for the for pulling in the case where f is not uniform, where it might be concentrated in certain regions, you partition it into these cubes, and then you look at each one of the cubes, and there'll be a larger or smaller number of points in each cube, and then you approximate that by a uniform distribution, and then you can go through the math and you can show that you get the required form, which is this right here. Okay, so continual limit of shortest path is we just published in the Annals of Applied Probability. I think it's out now. It might still be in press. But this result here for a similar type of limit, which is that if you look at the shortest path between any pair of points, and again, you make these assumptions, you have some compact support set with some positive definite metric tensor G that characterizes the curvature of the support set, and the path is pi that passes through this complete graph G between these 2 points, initial and final, initial and final. Then you get a convergence rate, which is n to the 1 minus gamma over d, and it converges to this integral here, which is a new distance between points. The distance between points that's along this weird relativistic path I was telling you about that depends both on the density function and it depends upon the geometry of the support set through this metric tensor G that is a function only of the differential of the path, which is parameterized by t, right? So this is a d-dimensional vector parameterized by t, and you take the derivative with respect to t of each one of the elements and look at the inner product, the natural inner product. It characterizes the geometry of the support set. So this indeed tells us that the curve is going to have minimal length, is going to effectively depend upon both the curvature of this underlying support set, the space in which these points live, and it's going to be inversely proportional to the density f. Gamma is always greater than 1 here, so this is a negative exponent, right? So where the density is high, we're going to tend to attract the path, right, to make this integral small. So where this density, the inverse density is high, the inverse density is high, that's going to make this low, and so that's going to tend to attract the path towards these high density regions. And hence this lensing effect that I was referring to a minute ago, and this just illustrates this property. So here's the uniform case, here's the Gaussian case, shortest path, the Archimedean shortest path shown against the relativistic shortest path when you use gamma equals 2 versus gamma equals 1 on the left for 2 dimensions. So that's, again, a continuum limit that we can, again, there are ideas behind the proof. I'm not going to go through these for lack of time, but it parallels the proof of the Beardwood-Hammersley theorem, at least in principle. The proof is actually a lot more difficult our paper in applied probability, journal probability, the annals of probability was about 40 pages long. So I can't go through that entire proof, but it's a very similar type of argument. That now the only thing that really changes is that if you have a path, a short path through the points, instead of spanning endpoints, it's going to span on the order of the dth root of n, right? So the multiplicative factor here, instead of being n times this 1 over dth root of n to the power gamma, is n, the 1 over the, the dth root of n, right? So when you get the exponent that comes out is indeed this 1 minus gamma over d. So there's a variational form. So here's where the PDEs come in. So we all know about the minimal path problem as having a variational interpretation. So if we perform this substitution, so I define this function f as a function of the path and the function of the derivative of the path as this integrand that I showed in that theorem I just displayed, then we can define the normalized shortest path length as the infimum over this integral, right? And so now you can simply use the calculus of variations, substitute for pi of t, pi of t plus delta pi of t, do the expansions, and then what you end up when you take the limit as that delta pi of t goes to 0 or is arbitrary, you find that the shortest path pi, the one that satisfies, that achieves this minimum, has to satisfy a system of decoupled Euler-Lagrange equations. There are generally d of them, only d minus 1 linearly independent equations. But so we have a time derivative here on the gradient with respect to the derivative pi dot of the path of this f function, and then we have a spatial gradient relative to the path function itself. So this difference has to be equal to 0, and the boundary conditions, of course, the path has to start at the initial point and then at the final point. So this is a standard elliptic equation that one could then seek to solve using methods like the ones we heard earlier on Monday, using box filtering and so forth. But for example, in this particular case, where you plug in this f, the variational PDE that describes the solution of the shortest path problem satisfies an equation which is shown here. And so you can see that if f is uniform, then the derivative of the path over a uniform the derivative, of that uniform distribution relative to any spatial variable is equal to 0. So you end up with the classic derivative of the path derivative divided by its magnitude has to be equal to 0. So that means the path has to be constant. That is a straight line, right? So you get back the straight line. In this case, for gamma equals 1, you also get the straight line. And in general, you have this linear combination of the gradients of the log likelihood, the score functions as they're called, of the underlying distribution that is going to serve as this attractor, this relativistic attractor that's going to change the straight line solution of this this PDE to a curved solution that passes through this or is attracted to the dense part of the distribution. So the special case that points in a plane, this boils down to a one-dimensional PDE, which is by parameterizing the path by t and y of t. And so now the derivative with respect to t really is trivial for the first component of the path, and only one of these equations determines the solution. And so you get this type of solution for the second argument, the dependent variable in the path description. With these coefficients, alpha 1 and alpha 2, the sum of the squares equals 1. And so this can then be solved using your favorite method. So what's the significance of this result? It's that solving a PDE on a fixed grid, right? Let's say you knew f of pi, or you could you knew the density, or you could approximate it using kernel density estimates, or your favorite histogram estimates, or what have you. Solving a PD on a fixed grid is order 1 relative to the number of points. Finding the shortest path is order n squared. So you've gone from a complexity order n squared to a complexity order 1, which means you can now find shortest paths using this type of PDE approach in very large databases, right? With billions of points, because as long as the density doesn't vary significantly, you then require only a relatively non-dense grid, right? Your grid has to be sufficiently dense so that you capture, up to the modulus of continuity of the underlying density function, and then you can just plug and play, right, without having to compute shortest paths through billions and billions of points. So that's the significance here, and this just is experimental validation. So how much time do I have left? Who's guarding the time? 5 minutes. Okay.
Only 2 minutes.
Yeah. So I'm just going to go very quickly through this other example, which is a multi-objective image retrieval. Instead of having one scalar function that's going to rank the images relative to the similarity of the image, the query image of my brother, right, in that sketch that my mother made, we're going to have multiple lists. So let me motivate this by going on vacation. So let's say that you and your partner want to go on vacation. You like the ocean, your partner prefers the mountains. So you want to find a vacation spot that incorporates both. If you go and look on Google Images for those great spots that satisfy your desire to be on the ocean, you'll find a lot of ocean images, but there's no mountains, at least in the top 8. Indeed, if you go down even to the top 40 or 100, you won't find mountains of any significance. Or your partner will go and search, and they'll only find mountains. So scalar searches over a multi-semantic description of the objective image that you're searching for, the one that has mountains and water, those types of descriptions can't be efficiently extracted by looking at 2 separate lists, right? Because each list can be arbitrarily long. It might be not be to the 1,000th or 100,000th in the list that you find the match that's going to satisfy both criteria. So that's just what this says up here. If you rank according to the mountain criterion and rank according to the water criterion, all of the images in the database, you won't necessarily find the one that's going to satisfy you and your partner. So possible solutions is using meta search or scalarization. Basically take the linear combination of the match, the similarities to your image of the ocean and your partner's image of the mountains, scalarize that down to 1, and then do all your sorting of image matches based on the scale parameter alpha. The problem with that is illustrated with this very simple example. Let's say that this is the similarity relative to the ocean image. This is the similarity axis relative to the mountain image. So we want to be down here, right? We want very close similarity. When similarity, we're talking about distance here. So the distance of your image to the image of interest should be down here for both you and your partner. And if you use scalarization, then you're basically going to, let's say alpha 0.1, then you're going to be ranking in decreasing importance as you scan through this set of points. And so you'll get a different ranking depending upon your scalarization, and you'll tend to miss the points in the middle. So as an alternative, Pareto fronts, which are non-dominated rankings, give you a peeling of the onion as opposed to a cutting of the onion. And so the question is, what's the behavior of these fronts? And there's a continuum behavior. So what I'm showing here are the fronts as we include more and more objects or images in the database. they get smoother and smoother. These are for different distributions on the features of the database. So you can see that we have these very smooth functions. And so we can show, again, that we get a limit as the number of objects in the database increases, a continuum limit for a optimization problem, Pareto front optimization problem, which is order n squared, that converges to the ranking, this Pareto ranking converges to the solution of the viscosity solution of a Hamilton-Jacobi partial differential equation. Just like we had an Euler-Lagrange equation before, now we have a Hamilton-Jacobi equation. It's a partial differential equation, and we can show that the solutions agree. The solution of the partial differential equation agrees with the actual construction of the Pareto fronts from the data better and better as the number of data points gets large. So that just shows some of the examples. And again, the significance of this is that now you can construct, if you use a fixed grid size for solving this Hamilton-Jacobi PDE, you can construct very fast ways of constructing Pareto fronts for large databases. You get order 1, right, as opposed to order n squared computation with these types of PDE approximations. I won't bother going through anything other than just showing a comparison for the runtime. If you use this type of PDE solver, you can go up to 1 billion samples, and the CPU time doesn't increase significantly because, again, it's order 1. Whereas if you use any kind of sorting combinatorial methods, the complexity increases as the number of objects in the database increases. So this just is an example of the power of PDEs, power of continuum limits for combinatorial optimization problems. So these are some of the references that I draw your attention if you want an easy introduction. This theory is introduced in this conference on information theory and applications. These are the hard math papers in science. Okay, so that's really all I have to say, other than the fact that there are lots of continuum limit applications I haven't talked about, lots of open problems, and we're just beginning to see, I think, the widespread application of these continuum limits to machine learning problems, data indexing problems, problems in characterizing geometry of very large numbers of features, and that I hope to be able to apply this to the artworks of my progeny and my relatives as we go forward. I haven't done that yet, so I don't have any results to show. So
Maybe we take one short question and leave other questions later.
all right.
Can you take gamma to be very large, to infinity, essentially, so that you're minimizing the length of the longest segments?
Yeah. So the theory I presented here, gamma has to be less than the feature dimension. So if you have very large feature spaces, then you can make gamma as large as you want, at least up to the feature dimension. But here you get a continuum limits, at least these continuum limits, only if gamma is less than dimension. Yeah. It's a good question. I don't know if continuum limits even exist in that case. Yeah. Maybe not. Yeah. Because it's only one edge. Once you start looking at things like diameter, right?
It's quite easy. You can do Dijkstra with the max.
With the max, right?
Rather than with the sum.
With the sum, yeah. But as you saw in the way we proved the theorems, the sum was critical, because that's what gave us this kind of law of large numbers, right? We have a sum. So max is going to be more like some sort of tail, large deviations type of result. So, yeah, I don't know. That's a great question.